a research and policy-informed discussion on cross-curricular issues within science and maths. One of the main purposes for a new primary curriculum in England was to encourage schools to make more cross-curricular links. According to Teach Primary, the best primary practice includes a blend of rigorous, discrete subject teaching and equally effective cross-curricular links. Both approaches are needed for effective learning. It is helpful to think about cross-curricular links in two ways. First, there are links where children use and apply aspects of learning from one subject in another. The second type of link is where one subject provides a context for developing learning in another. Similarly, Haylock and Thangata state that cross-curricular mathematics can be understood in three ways. The first is that other areas of the primary curriculum can be seen as providing opportunities to use and apply the skills and knowledge that pupils learn in maths lessons in purposeful activities. Second, other curriculum areas can be seen as providing meaningful contexts within which mathematical concepts can be introduced or developed. And finally, mathematics can be seen as a number of curriculum areas that might come together in an extended cross-curricular project of some kind. In this case, this presentation will concentrate on the application of mathematical understanding in science and how learning in both subjects can benefit the children in their education. According to the Department for Children, Schools and Families, subjects will be complemented by worthwhile and challenging cross-curricular studies that provide ample opportunities for children to use and apply their subject knowledge and skills to deepen their understanding. There are times when it is right to marshal content from different subjects into well-planned cross-curricular studies, and by doing this it provides opportunities across the curriculum for children to use and apply what they have learnt from the discrete teaching of subjects. There are many theorists who agree that cross-curricular links between maths and science are important. The new national curriculum suggests that all teachers should develop pupils' numeracy and mathematical reasoning in all subjects, so that they understand and appreciate the importance of mathematics. Mathematics is a creative and highly interconnected discipline that has been developed over centuries. It is essential to everyday life and critical to science. The new curriculum also states that a rich quality science education provides the foundations for understanding the world through the specific disciplines of biology, chemistry and physics. The Department for Education expresses that pupils should apply their mathematical knowledge to their understanding of science, including presenting and analysing data, which is the focus topic for this presentation. Hitchcock also agrees that science can provide a wonderful opportunity to practice a variety of math skills within an engaging context, for example, measuring and presenting and interpreting data. Alongside these specific math skills, using and applying these skills will be reinforced through problem-solving, communication and researching, which is required in any scientific investigation. Louis also suggests that for younger children, numbers enable them to talk about their science. It helps them to explain their findings. Therefore, the beginning of early counting is intrinsic to their understanding of the world which they engage in as scientists. Louis also suggests that both science education and cross-curricular approaches to teaching and learning are informed by a constructivist view of learning, and that a feature of constructivism is that effective learning occurs when children make links between new ideas and their own past learning or lived experiences. However, there are some that do not quite agree. Brown states that quantity and quality do not often go hand in hand. He suggests that less time spent on maths and less maths curriculum coverage may allow teachers and children to become more competent and confident, albeit with a smaller range of mathematical ideas. Brown further notes that the key issues are whether we can establish a consensus in terms of coverage, depth of understanding and application. In 1998, the Department for Education defined numeracy as knowing about numbers and number operations. They said that as well as developing an ability to solve number problems, children are expected to become familiar with the ways in which the numerical information is gathered by counting and measuring and is presented in graphs, in charts and in tables. Clearly, it is in this last aspect that links with science that has the most to offer. The Department for Education believe that numeracy skills can be developed and practiced in relevant scientific contexts. Investigations which generate from data recording, manipulation and interpretation use numeracy skills. At the same time, numeracy supports the search for patterns and relationships, which is crucial for underpinning the construction of conceptual understanding. Therefore, data handling in science is a critical area for children in both numeracy and science. Jarvis in 2009 suggested that science provides an ideal opportunity to enable pupils to apply and understand mathematical ideas, particularly data handling. The challenge is to match science skills and conceptual development with pupils' mathematical development. The Department for Education in 1998 agreed with this and similarly suggested that it is important that teachers ensure that the children's mathematical experiences match what is needed for the science investments. They must ensure that their prior knowledge is adequate. Newton in 2000 also agreed, and he suggested that teachers will need to match the learning experience that they offer the children with what they judge to be appropriate according to their needs, abilities and interests. As we know, mathematics contributes to many subjects of the primary curriculum and often in practical ways. According to the Department for Education, activities such as recording the growth of a plant, measuring temperature and rainfall can provide data for starting points for discussion in maths lessons, as well as opportunities to apply and use mathematics in real contexts. According to Haylock, pupils should be taught to select and use data handling skills when solving problems in other areas of the curriculum, and in particular science. All stages involved in handling data: collecting it, organising it, representing it and interpreting it. Pupils should learn how to collect data as part of a purposeful inquiry, setting out to answer specific questions that they might raise. However, the children need the pedagogical knowledge prior to this. The children should be taught about data handling in maths before the teacher organises a scientific investigation in which they can then apply these new skills and develop them further. Without this pedagogical knowledge, the children may find it difficult to address all four stages involved in handling data. Therefore, in this context of data handling, mathematics is a crucial element to science. For example, data handling can be developed as part of a science-focused project in Year 6 on the effect of exercise on the heart. In terms of making cross-curricular links, this activity links with maths and physical education. Before the children begin, they need to decide what data is needed, how to collect the data, and how to represent the data. In this particular activity, the children would measure their heart rate by counting their pulse at different times during a physical activity. They would measure their heart rate at rest rate, straight after exercise, and every 2 consecutive minutes thereafter. The children will need to measure and record how many times their hearts beat per minute. A useful mathematical technique on collecting the data is to record their results in a table. However, as previously mentioned, this is a skill the children must acquire in their maths lessons first in order to develop their skills further through practice. Another mathematical skill is the children will need to have is to be able to count their beats accurately and measure it against a specific time using either a stopwatch or clock. Once the children have collected their data, they will then need to present it using graphs. In this case, it is expected that children would use either a bar chart or a line graph to present their data, but again the children must have the mathematical knowledge to understand why this particular graph is the correct one to use. The children would then interpret their data and would be expected to find that their heart rate was highest straight after physical activity and the lowest at rest rate. It is expected that the children would relate their results and findings to their hypothesis to see if they had predicted correctly, thus enhancing their subject knowledge. The children can use their ICT skills to present their data by creating their charts using Microsoft Excel. This then provides another cross-curricular link to ICT. According to Newton, when children carry out surveys or collect a lot of data, the advantages of ICT is immediately apparent. Newton suggests that data handling also requires the search for patterns and interpretation of the data to reach conclusions. The data can be qualitative or quantitative, and in this process the children learn about measurement and quantities and explore number using spreadsheets, which helps them with mathematical and graph work. Since children must demonstrate their ability to do this in scientific investigations, the application of science skills like classification, observation, prediction and interpretation to information stored and classified in a database is an excellent extension of those same skills used in practical activity. Brown in 2003 also agreed that the use of ICT can support the children's development. He suggests that the use of ICT in maths is challenging but exciting. Developments like interactive whiteboards present really powerful opportunities for teaching mathematics, thus benefiting, supporting and encouraging the children's pedagogical development. However, there are some disadvantages to using ICT in a cross-curricular way. Byrne and Sharp suggested that when teachers plan for the use of ICT in their science lessons, what can be achieved is clearly determined by the resources and facilities that they may have at their disposal. For example, when the children are timetabled to do science, the school's shared computer room may already be booked out to another class. To resolve this, the teacher would need to plan carefully to ensure adequate timing to arrange the use of ICT suite. Another issue may be that the school does not have a shared ICT suite, and the pupils may only have access to one computer that is based within the classroom. This would then prove difficult and would be time-consuming to ensure each child records their data using Microsoft Excel. The teacher could resolve this by teaching the children how to use Excel as a class, and then could pair the children up and ask the teaching assistant, if available, to assist the children to interpret their results. According to the Department for Education, ICT is seen as increasing the pupils' confidence and motivation by making schoolwork more enjoyable. In conclusion, from this presentation, I believe that cross-curricular links between science and math is important to children's education. As teachers, we should continue to approach these subjects in a cross-curricular way, as proposed by the new national curriculum. However, I do believe that it is vital that the children